talking about Atlas. Many of us know Lauren. She was an undergraduate and graduate student here at Berkeley, so we're really excited to welcome her back next week and hear about her work on Atlas experiment. So it is also a pleasure to introduce today's speaker, one of our own faculty members, Professor Feng Wang. Feng Wang received his bachelor's degree from Fudan University in Shanghai and went on to do his PhD at Columbia University with Tony Hines, who many of us know very well. Feng Wang came to Berkeley as a prestigious Miller postdoctoral fellow, and then we snatched him into assistant professor position in 2007, is that right? He went on to receive just about every prestigious award that a junior faculty member can receive. He was an NSF Early Career. He won the NSF Early Career Award, the DOE Early Career Award, the Presidential Early Career Award as well. He was a Sloan Fellow and a Packard Fellow. Is that all of them, more or less? And so that is a really outstanding record of achievement. So I will let Professor Wang introduce his own topic today. So join me in welcoming Professor Feng Wang.
Is it better? Okay, thank you. Oh, thanks, Steve, for the introduction. And it's really a great pleasure to give the colloquium at home. And today I will tell you a little bit of our work trying to study Dirac electron physics in graphitic materials. Graphitic carbon material has been a focus of physics study for many centuries. It started with three-dimensional graphite, but later it was realized that there are actually many different allotropes of graphitic materials, from zero-dimension fullerenes, which has only 60 carbon atom, to a one-dimension carbon nanotube, which has a diameter of 1 nanometer, but length can be micron or millimeter long, to graphene, which is a 2D membrane that's single atom thick. We know that in physics, dimensionality can play a tremendous role in terms of physical phenomena. And these carbon allotropes really provide a rich platform for us to study how different phenomena can emerge at reduced dimension. Although experimentally, the two-dimensional graphene was discovered the latest, it actually is the easiest to describe and provides a starting point for us to understand this graphitic material. So let's take a look at graphene. So since its discovery about a decade ago, graphene has been explored extensively, both in physics and in engineering. The reason, part of that is because graphene has rather remarkable material properties. For example, it is a single atom thick membrane, but mechanically is extremely strong. It has the highest room temperature mobility, as well as very good thermal conductivity. So it's it has great potential for applications. But in physics, what makes graphene really interesting is its unique electronic structure. So we think in the real space, graphene is described by this two-dimensional hexagonal lattice. So the band structure is described in momentum space. So in that case, we think of the delocalized pi electron of the graphene. When it sits on this hexagonal lattice, it actually forms this conduction and valence band that touch each other at these special points known as K and K prime points. As you can see that there are 6 points over here, but 3 of them are really identical because they are connected by the reciprocal lattice vector. So they are really just 2 copies of the kind of Dirac points. And we sometimes call them K and K prime valleys. So most of the electrical as well as optical properties of a material are dominated by electrons close to the Fermi surface. That means close to this crossing point. As a result, we can simplify the overall band structure by zooming in into these special points. And then basically we get 2 copies of the so-called Dirac cone, where vertical axis is energy, and kx and ky is the horizontal plane. And k and k prime can be related by time reversal symmetry. So once you know the behavior on one value, you can immediately know what happens in the k prime value. Just think about time reversal symmetry. So we'll focus on the behavior of a specific value first. So as you can see from this dispersion relation, we can easily tell that energy is proportional to momentum. That means when electrons are moving in this hexagonal lattice, the behavior becomes very different from a regular particle where energy is proportional to momentum squared. Instead, this dispersion reminds of us about photons. So that means these electrons moving in this hexagonal lattice actually behaves like massless particle, and they are known as massless Dirac fermions. One key signature of this massless Dirac fermion is the so-called pseudo-spin degree of freedom. So let's try to understand it. First, we look at the lattice of the graphene. What we can see is within a single unit cell, there are 2 kind of symmetric atoms known as A and B sublattices. So if you want to describe the electron wave function of graphene, you have to consider 2 parts. One is the overall envelope wave function that averaged over a unit cell. And then within a unit cell, you have to describe the kind of amplitude at A and B sublattice. So you can consider this is effectively a 2-component internal degree of freedom. And whenever we have 2-component degree of freedom, we can map it to spin 1/2, like spin language, or known as pseudo-spin. If you use the pseudo-spin of the AB sublattice, we can write down the Hamiltonian of the system in a quite simple fashion. It simply equals to H equals to Fermi velocity times pseudo-spin dot product with the momentum. So now we can get the dispersion relation of the system directly by asking what are the eigenenergies for a given momentum. So here you can see the momentum kind of plays the role of magnetic field. So the eigenenergy corresponds to pseudo-spin parallel or anti-parallel to the momentum. And that really gives us the conduction and the valence band. So for a given momentum, you have an electron that has pseudo-spin parallel to the momentum. That's the high energy state or conduction band, or an electron that's anti-parallel to momentum, that's valence band. So what you can see is when you look at the pseudo-spin distribution in momentum space, it actually has a quite unusual texture. So all these pseudo-spin are parallel to the momentum, and all these pseudo-spin are anti-parallel to momentum. So this happens for the k value. So if you think about k prime value, you can just do a time reversal symmetry, but similar behavior happens. And this unusual texture of pseudo-spin in momentum space really gives rise to a lot of exotic behavior of electrons in graphene. For example, or we can think about a simple tunneling problem. So conventionally, if you have a particle coming in with finite kinetic energy, and it hit on a potential barrier that has energy larger than kinetic energy, we know that quantum mechanically, the particle still has some probability to tunnel through the barrier. However, the probability decays exponentially if you have a wide barrier or a very tall barrier. However, if you have a massless particle like electrons in graphene, things become very different. So when you have an electron with finite kinetic energy coming in and see a barrier, or when the barrier potential is too high, it can actually convert into an antiparticle and go through the barrier without exponential decay. And at the end, it converts it into electron again. And what's more amazing is at the reflection point, the forward electron and backward electron have opposite pseudo-spin. So they can actually not backscatter. That means all the electrons will convert into antiparticle and go through the barrier. So in this case, you actually have perfect tunneling, even if you have a very tall, a very wide barrier. And this is known as like Klein tunneling behavior. Another example is when we think about this pseudo-spin texture in momentum space, you can imagine when the electron actually move around and have the momentum go around 360 degrees, although the wave function come back to itself, they actually pick up a negative sign, just like regular spin 1/2 system. When you go around 360 degrees, you get a negative sign. That corresponds to a phase change of pi, known as Berry phase of pi. And this Berry phase really leads to the so-called anomalous quantum Hall behavior in graphene, where when people see quantized Hall conductance, it's quantized at half integer value because it's shifted by this pi Berry phase rather than a regular integer quantized Hall effect. So this exotic behavior associated with massless Dirac electron has been studied quite extensively in our last decade. Today, I would like to add a little bit twist to this Dirac electron physics that go beyond what happens in monolayer graphene. And the first example is to generate a finite mass and study massive Dirac electron physics in the context of bilayer graphene. And the other one is to study how the Dirac electron behavior change when you go to one dimension, say when it's confined in a carbon nanotube. So let's start with the first topic, to generate a mass and create a massive Dirac electron. Theoretically, it's very easy to do. All you need to have is basically an extra term that is diagonal, where you have different potential at A and B sublattice, so delta and negative delta. In this case, what you can see is even at 0 momentum, the eigenenergy is non-zero anymore. The eigenenergy is delta and negative delta. That corresponds to opening up a semiconductor band gap. And in that case, the electron and hole has opposite energy. And in order to create an electron-hole pair, you need to put in 2 delta here now. And in the language of high energy physics, basically this can be described effectively as massive particle, because to generate a particle-antiparticle pair, you need to put in finite energy. And from Einstein relation, the effective mass can be defined by the energy you put in delta divided by speed of light squared. And in this problem, the linear dispersion speed of light is actually described by Fermi velocity. So it will have this expression. So, or you might wonder, why do we care about studying massive Dirac electrons in graphene when we have massive Dirac electron in our everyday life? And the answer is, if we can do it in graphene, we can actually control the mass experimentally and potentially other parameters. And that really allows us to kind of answer different type of questions. For example, you can ask, what happens to the pseudo-spin degree of freedom? We know at very high energy, it becomes more like a massless particle. So pseudo-spin will be locked to momentum. So it turns out when you open up a band gap where the kinetic energy becomes much smaller than the band gap, that's like a non-relativistic limit. In that case, pseudo-spin actually decouple from momentum, just like real or electrons. When you go to non-relativistic limit, you actually have a spin that's independent with momentum. So in this case, the pseudo-spin also actually flip up. And associated with this pseudo-spin, it has a finite Berry curvature. So just like real spin, it will actually have a finite angular momentum as well as finite magnetic dipole, as predicted earlier by this initial theoretical paper. And in addition, you might ask, if we can create a finite mass from 0, we actually have a choice to have positive finite or negative finite. So, or what does it mean if we can actually create a negative finite mass? So in order to explore this problem, we first need to generate a mass term, or basically create a band gap in graphene first. And to do that, we make use of the bilayer graphene. It turns out naturally the lowest energy state for bilayer graphene has this so-called A-B stacking or Bernal stacking, where the A atom on the top layer sits directly on top of the B atom on the bottom layer. So there is some intrinsic way to recognize the A and B sublattice. So once we have this bilayer, the electronic structure becomes quite different due to the interaction between the top and bottom layer. So instead of this linear band, we now have 2 parallel conduction bands and 2 parallel valence bands. To understand this band structure, we can first focus on the K point and see what are the eigenenergy states that look like. So first, in this case, we have 4 atoms in a single unit cell, top A and B atom, and bottom A, B atom. Since the top A and bottom B sitting directly on top of each other, so they strongly hybridize and form a bonding and anti-bonding state. So that means you have energy repulsion. They move to a low energy state and a high energy state. However, the top B and bottom A atom don't interact with anything directly, so they keep the initial energy at 0. So now we have 2 degenerate states here and 2 split states here. If you include the dispersion as a function of momentum, you recover these 2 parallel conduction bands and 2 parallel valence bands. So what we see is in bilayer graphene, although you recognize the AB sublattice, the band gap is still 0. There is a degeneracy due to the top B atom and bottom A atom. So in order to create a finite band gap, we need to break this degeneracy. However, in bilayer graphene, this becomes very easy to do because now these 2 atoms are sitting on 2 different layers. One can lift the degeneracy simply by applying an electric field vertically. So you can imagine if you apply a vertical electric field, the potential at this point and that point becomes different. So that's a diagonal term with different potential, and it creates basically a finite band gap in this system. If you apply electric field in a piece of graphene, like in a typical field effect transistor, it turns out you can also control its carrier concentration. So in bilayer graphene, we actually have a quite unique system where you can have a continuously tunable semiconductor band gap as well as tunable carrier concentration simply by applying electric field. And the band gap and the carrier concentration are 2 most important parameters that describe a semiconductor. Of course, you would like to control this carrier doping and band gap independently. And that can be achieved in bilayer graphene in a fairly straightforward fashion. If you can control the electric field above and below bilayer graphene independently. For example, if we want to just create a finite band gap and keep the carrier concentration to be 0, we can have a field distribution like this, where the field above and below are the same. In this case, we can see the field are continuous above and below. From Maxwell equation, we know the total charge in the system has to be 0. So we have 0 doping. But this field obviously breaks the immersion symmetry, so we have a finite band gap. On the other hand, if you want to add the doping in the system but keep the band gap to be 0, you can have this type of field configuration. You can see it preserve the inversion symmetry, so the band gap will be 0. However, there are a lot of field lines terminated in graphene, so it will be strongly electron doped. So if you want to combine finite doping and finite band gap, basically we can mix the configuration of these 2 types of electric field. Experimentally, to achieve this field control, we can just have a dual-gated bilayer graphene device as illustrated here. So you can see this kind of a gray area is a piece of bilayer graphene that one can make. And then you use a top gate to kind of control the field above graphene and a silicon back gate to control the field below graphene. So this shows a side view of how the device looks like. You have a piece of graphene here, and you have a top gate where by applying the voltage between top gate and graphene, so you can think this as a capacitor, so you can control the field above graphene. And when you apply a gate voltage between silicon and bilayer graphene, then you can control the field below the graphene. So once you have this control, basically you can create a band gap or change the doping. Let's focus on the case where we keep the doping to be 0, but just open up a finite band gap by applying larger and larger electric field. So one way to determine the size of the band gap is to do direct optical spectroscopy of the system, because when you open a band gap, you can imagine there should be new optical transition appearing at the band-to-band transition. So you should see a new absorption peak when the band gap becomes finite. So here we show the experimental data where we measure the absorption difference between gated sample and ungated sample as a function of kind of probe photon energy. And you can see when you apply larger and larger electric field, there is a broad absorption peak showing up. That actually corresponds to the band-to-band transition. So neglect this very sharp feature, which comes from a special coupling between phonon and electronic transitions. So by simply measuring this broad absorption peak, we can determine how big the bandgap is. So in this case, basically, we can open up a semiconductor bandgap in the order of 200 millieV. So now when we create a finite bandgap, that really corresponds to create a finite mass if we define mass as the energy you need to create the particle divided by Fermi velocity squared. So if we create a finite bandgap in bilayer graphene, we can think effectively we are generating a massive Dirac electron particle. So OK, so with this finite mass, what we can play with it. One particular interesting question is the effect of opposite electric field, because as we mentioned, if you apply electric field, you create a different potential between A and B kind of sublattice. And we can define the mass basically equals to delta divided by VF squared. So for a given delta, we get a given rest mass. Now, if we change the electric field direction, we effectively change delta, right? So that means we'll change the sign of delta or the sign of rest mass. So what does it mean when you have a negative rest mass? As you can see, looking at these two pictures, they're actually symmetric to each other. That means if we look at the energy spectrum, the negative rest mass system and positive rest mass system, they should behave in the same way. So it turns out if you look at Dirac equation itself, if we say in our world, the rest mass of the electron is negative, there's actually no direct measurable consequence if we only live in a world with negative rest mass. So the special thing happens when you start to combine the two worlds together. One side has positive mass and one side has negative mass. In that case, we not only need to look at the energy spectrum, we need to look at the wave functions and how they connect with each other. And one found out that at the boundary of these two different worlds, there will be a topologically protected new state that shows up that guaranteed to be zero mass around here. So this actually has been studied first in the high energy physics scenario, and is related to the so-called fermion domain wall problem. More than 30 years ago, it was shown that theoretically, if you can imagine two worlds, one side has a positive mass and one side has negative mass. So at the boundary of these two worlds, no matter how this positive mass side and negative mass side match, you are guaranteed to have a massless particle living at the boundary. And if you have 2D to 1D transition, the massless particle is actually kind of strange in the sense it will propagate along a single direction. And if you have a 4-dimensional mass domain and a 3-dimensional boundary, turns out the massless particle will actually have single chirality or single-handedness. And this single-handedness massless particle is actually just like neutrinos in our standard model. So it was later found out that if we want to simulate standard model on our computer, the only way to do this lattice QCD and simulate things like neutrinos is to embed our world actually inside of like a 4-dimensional kind of domain with opposite mass. And there are even theoretical speculations that we A and B sublattice. So one way to do that is fix the A and B atom and field. But an alternative way to do that is actually switch the position of AB atom, but keep the field to be the same. For example, it turns out we can have these two different kind of stacking working. One is known as AB stacking, one is BA stacking. Effectively, we just shift the top layer atom slightly relative to the bottom one. So in this case, you really revert the position between A and B sublattice. So in that case, even if you apply a homogeneous electric field everywhere, you actually effectively create object mass on the two sides, and then you'll generate a mass, basically a mass domain wall and a massless particle living at the domain wall. So we might wonder how can we create such a structure. It turns out they really exist already in nature. So this was first observed in transmission electron microscopy studies. But here, the Cornell shows in TM diffraction, the AB stacking and BA stacking actually can have different diffraction intensity. So you can visualize them very easily. And if you do a high resolution TM imaging, you can really see the effect position of the atoms. So basically, if you have AB and BA stacking, you can see this well-defined kind of position of atoms. And if you have the domain boundary in the middle, you can see there is a kind of a transition area, and it matches basically with the simulation. So what you can imagine is the top layer graphene and bottom layer graphene. The top layer is stretched very slightly relative to the bottom one by about 1 unit cell size. Instead of homogeneous strain across the whole top layer graphene, it actually would like to keep the AB and BA stacking in most of the place because it lowers the energy. So it wants to concentrate the strain in the middle. So it's really a balance between the strain energy and this stacking energy determining how wide the kind of domain wall is. So experimentally, it was found the domain wall has a size about 4 to 10 nanometers. And that's really perfect for our kind of study because this is narrow enough that you can think this domain wall to be a very well-defined 1D structure. But at the same time, this is actually large enough. This is actually about 40 times of lattice constant. It means the domain wall is a smooth variation. So it's not an atomic defect, and it does not mix the K and K prime value. So we can talk about specific value physics very well. So, however, the TM sample was not easy to use for transport measurement because the electron beam tends to damage the suspended bilayer graphene. So what we need to do is have an alternative way to see these domain walls, but in a non-destructive fashion. And the approach that we turn to is the near-field optical spectroscopy. So the idea is we can shine light onto an AFM tip that is coated by metal. So when the optical light hit on the tip, especially infrared light hit on the tip, the electromagnetic field gets dramatically enhanced right below the tip due to effectively the antenna effect. So as a result, when we measure the scattered light, we can actually preferentially measure the material right below the AFM tip. So we would be able to measure the optical response, but with a spatial resolution of 10 nanometers rather than the wavelengths of the system, which can be 1 micron or many microns. So in this specific case, 6 micron. And when we have this optical contrast at nanometer scale, we can actually visualize this domain wall very nicely. So here we show a regular AFM image where you look at the topography. So when you have this kind of domain wall in bilayer graphene, the topography doesn't show anything. It's just a smooth bilayer graphene. However, when we look at the optical contrast, you can see these bright lines go through the bilayer graphene. They really correspond to this stacking domain fault between AB and BA sublattice. Once we create this domain wall, we can try to, say, look at the transport or conductance along this domain wall. So this is a typical structure that we make. So the white dashed line corresponds to the bilayer graphene that we cut into the specific shape. And then we can put a lot of electrodes to measure the conductance through it. So in this case, between 1 and 2, we'll measure conductance through a piece of bilayer graphene with domain wall. So the green line shows where the domain wall is. And between the electrodes 4 and 5, for example, it will be a reference sample where you measure only bilayer graphene without domain wall going through it. And here we show the transport data. If we look at a piece of bilayer graphene itself and measure resistance as a function of applied electric field across the graphene, what we can see, the resistance keep going up with applied electric field. So what happens is the vertical field create a finite band gap, and when you have larger and larger band gap, larger and larger electric field, the band gap increase and the graphene becomes more insulating. On the other hand, when you have a domain wall, what we can see, the resistance initially increase because the bilayer graphene becomes more insulating, but very quickly it actually saturates. So that means when the bilayer graphene becomes insulating enough, all the conductance is dominated by this domain wall. And it shows really along this domain wall, there is a well-defined conducting channel. To look at the conducting channel more, we can actually measure the conductance as a function of the length of the domain wall, which is simply defined by the width of the top gate. So here we show that the conductance all lies in the order of quantum conductance E squared over H, but it still has a finite length dependence. The overall length dependence can be described by the so-called Landauer formula. Basically, G equals to a quantized value times length dependence. So if there is no backscattering at all conductance should be quantized by E squared over H. So in this case, there will be 4 conducting channels. However, in this system, there are still finite backscattering. So it will have a kind of length dependence. And the scattering length is defined by L0, which is about 400 nanometer over here. And this observation is really consistent with theoretical predictions, where it was predicted that in bilayer graphene, in each valley, you should have 2 helical modes. And each mode is also spin degenerate. So there should be really 4 conducting channels. So along this domain wall, basically, there should be 4 conducting channels moving forward that lives in us only at K value. And that basically gives us the kind of conductance that we measure. And an interesting aspect of these conductivities is not only an electrical current where the charge moves forward, because all the electrons living in a single valley is also a valley current. So we are trying to now explore the possibility to actually measure the consequence of this valley polarization of these electrons. OK, so that's the first topic where we study kind of massive Dirac electron in bilayer graphene. Next, I would like to turn to what happens if we look at a one-dimensional object like carbon nanotube. Carbon nanotube, to some extent, is the best 1D system that you can think of. It has a diameter about 1 nanometer, but the length can be millimeter long. And in addition, this kind of system actually is almost defect-free. You can have almost perfect structure along the nanotube. And so to think about the electronic structure of the nanotube, we can actually think about rolling the graphene up. And through the quantization of the state, basically, we can have both semiconducting and metallic carbon nanotube. And they depend very sensitively on the structure. So for example, if we have a nanotube look like this, so it has something known as 11.9 chiral index, it will be semiconducting. And if you have a nanotube like this, 10.10, so it will become metallic. So in our study, basically, we'll need to focus on this metallic carbon nanotube. So, OK, so the electrons living in 1D metal turns out to be very different from the electrons in 2D or 3 dimension. If you think about kind of regular metal, although the electron can have a Coulomb interaction, but we can actually approximate the whole system as a quasi-free electrons, and everything can be described by the Landau's Fermi liquid theory. You can think electrons to be largely uncoupled with each other. However, when you have electrons in 1 dimension, the electron-electron interaction becomes extremely important. And and one way to think of that is think of a one-lane highway where when you think about the cars want to move forward, it actually has to push all the cars around. As a result, you can only have collective motion of the cars. You cannot have a quasi-free car move around. And similarly, the electron basically always move in a collective fashion, and is described by the Luttinger liquid theory. And in the Luttinger liquid theory, it actually has predicted many interesting phenomena. And one of them is because you don't have a quasi-free particle, that means you don't have a particle that has well-defined energy and momentum at the same time. So if you look at the spectrum of the energy distribution, it will have a power law distribution. And another interesting aspect of the Luttinger liquid is the collective excitation. They will have a charge mode and a spin mode, and they naturally separate from each other. So spin mode is known as spinons, and charge mode is known as plasmons. So because the spin-spin interaction is relatively weak, so the spin will propagate at more or less the free particle velocity, so Fermi velocity. However, the plasmon will move at a much higher speed because the strong electron-electron interactions. So Luttinger liquid physics has been, in nanotube, people have tried to study it even a long time ago. Actually, I'm going a little bit slow, so I will skip a few of these. And I will just focus on, so in our case, we'll try to study the kind of separation of the spinon mode and the plasmon mode. In particular, determine the velocity of the plasmon excitation. So it turns out to excite the plasmon in carbon nanotube, we actually cannot just do a far field measurement because it was predicted the plasmon wavelengths is much, much smaller than kind of free space wavelengths. So there is a very large momentum mismatch. In order to excite these plasmons, again, we turn to the near field optical study where we can kind of shine light on AFM tip. Since the AFM tip can provide a large momentum mismatch, it can basically excite the plasmon. And when the plasmon propagates along the nanotube, it can be reflected and set up basically these periodical oscillations, and that allow us to visualize the plasmon in real space. So we kind of try to go ahead and do the measurement, and it's really quite amazing that for a single nanotube where the diameter is 1 nanometer large, you can actually see this very well-defined oscillation of the plasmons. And from this oscillation, we can directly determine the plasmon wavelengths, and from that, you can calculate plasmon velocity. So here, basically, we just show example that we can look at the plasmon excitation in the nanotube with different excitation wavelengths, or you can look at different nanotube and see how the plasmon wavelengths actually change. So what we found is the plasmon velocity, as shown here, that actually has an interesting distribution over here. So this distribution turns out to be related to how many nanotubes we have in a specific bundle of nanotube. So all individual nanotubes will have about the same velocity. And when you have like a 2-tube bundle, it will have velocity described by square root of 2, and 3-tube bundle will be square root of 3. And in particular, if we kind of calculate, so from the wavelengths of the plasmon, we can calculate the velocity by wavelengths divided by frequency, which is basically the excitation laser frequency. From that, we can determine the ratio between plasmon velocity and the Fermi velocity, and we can see that even for an individual nanotube, the ratio is like 3.5. That tells us that the plasmon velocity is indeed strongly renormalized, and there is a very strong electron-electron interaction. So I will not go to the theoretical description, but just say the ratio of the plasmon velocity and the kind of Fermi velocity actually directly tells us how strong the interaction is, and it allows us to determine this Luttinger liquid parameter, which equals to 0.27. And the other interesting thing about the plasmon in nanotube is actually is really strongly confined. So even when we use a 10 micron excitation, the plasmon wavelength inside the nanotube is about 100 nanometers. So there is a confinement about 100 times. But when we think about the field in the kind of transverse direction, it decays even faster, because in a 1D system, the electric field decay as 1 over r, so it will decay around the diameter of the nanotube. So there's a confinement more than 1,000 in transverse direction. So if you consider the mode volume, so we have lambda over 100 divided by, multiply lambda divided by 1,000 squared. So this actually, plasmon is confined by about 10 to the 8 times compared with a free space photon. But at the same time, they actually have very well-defined oscillations. So it actually, although it's extremely strong, very strongly confined, it actually has quite high quality factor. So that allow us to potentially use it for kind of plasmonic waveguide and sensing applications. Or with that, I would like to just skip to the conclusion. I have shown you basically the graphitic system is actually a very nice platform that allow you to study the different type of behavior. In particular, for bilayer graphene, that allow you to controllably generate a mass and realize a mass domain wall and to study its transport property. And in carbon nanotube, basically, is kind of the best system that you can explore the Luttinger liquid physics. And with that, I would also like to thank the student and postdoc who did the work, and also other members of my group whose research I didn't cover in this talk. We also benefit with strong collaboration with many faculty in the department, in particular, Professor Cromie, Louis, Shen, Zetto, and analyzers, as well as discussions with Professor Moore, Lee, and Vishwanas. And we also benefited a lot from advanced light source. And with that, I thank you for your attention.
So, Professor Wang, let's plenty of time for questions. So, I'm curious about the negative mass layer.
Okay.
So when you get negative mass, does it show any other properties of what we theoretically call negative mass?
Oh, I mean, so this negative rest mass, so you can actually look at the Dirac equation itself. If you just assume the rest mass to be negative, just by itself, if you solve the equation, you actually have no other consequences. It will give you exactly the same behavior as you have a world with positive mass. So the only interesting happens is when you try to bring this world together.
And like you expect, instead of gravitational attraction, gravitational repulsion.
Oh, okay, that's a very interesting question. That's certainly not relevant to all the condensed matter physics problem. But yes, okay, so in terms of real high energy physics, I guess in Dirac equation, basically, we don't think about gravity. So so everything looks the same. But indeed, if you have gravitational force, I don't know what will happen. We have to ask our kind of high energy physicist what it should be. So for 1D nanotube, because the kind of the electron is very strongly confined in a nanotube and it moves in one direction, I think it will not be strongly affected by magnetic field because the magnetic field cannot really deflect or change the motion of the electron directly. So to the first order, I think the effect will be negligible. So that's very interesting. So actually, for this one-dimensional nanotube, this Dirac electrons, the dispersion of the plasmon is strictly linear. So basically, the velocity is constant. All the plasmons, no matter what energy it is, the velocity is actually constant. So that's very different from like a 2D case or 3-dimensional case. Okay, so the question is, what's the exact Hamiltonian of bilayer graphene when you create a finite mass? So the way I described, I kind of try to simplify it a little bit. So in reality, the kind of when you open a band gap in bilayer graphene, the kind of a delta and the negative delta term is the same. But the off-diagonal term, instead of sigma dot p, you actually have sigma dot p squared. So, although the details are a little bit different, but the kind of overall picture of the physics remain the same. So the fact that you have inversion of the band and the topologically protected boundary state, they are exactly the same.
One more question?
Oh, in the zero dimension case, basically everything is kind of quantized. So you actually have kind of discrete states and discrete transitions in like in carbon-60. So to some extent, it's less interesting because you cannot look at a lot of the effects related to transport and so on and so forth.
Okay, well, let's thank Professor Wang. That was great.
Oh, did I go too long or like?
No, you were fine.